Cosine series, you use the properties of i's, you take a step back, you go, shit, that's just a sine and cosine function, right? With an I out front. And fortunately for us, the I didn't matter because we got 0 here, right? So we kind of got lucky there. All right, that's it. So you've now seen where the most beautiful, arguably the most beautiful equation in math comes from. Okay, next problem I'm going to do. How are we doing on time? 2 o'clock? Okay. Oh. I know it sounds pathetic. I'm up here like winded erasing the board, but these markers like are almost permanent markers, I swear. I need like a buffer machine to get them off the board. I'm going to go to Wolfram Alpha real quick, I think. Where's my menu? No, bookmarks. I'm going to go to Wolfram Alpha, and I'm going to do integrate e raised to the negative x squared. Okay, so when we ask Wolfram Alpha to find the antiderivative of e to the negative x squared, it has a major problem. It says the answer is 1/2 square root of pi erf x, and erf is the error function. So it cannot give us a nice answer. It can't, all right? And I think you all agree, like Wolfram Alpha is very powerful, so if it could do it, it would do it, right? So now what I'm going to do is I'm going to say integrate it from 0 to 1. So instead of an indefinite integral, a definite integral. See that decimal answer? How did it get this, right? How did it get that decimal answer? Well, I'll show you how it did it. We're going to do it right now. We are going to do the integral from 0 to 1 of e to the negative x squared dx. So there is no easy way to integrate that. I think I convinced you with Wolfram Alpha that you can't do it, we're not going to be able to do it. But instead of writing e to the negative x squared, I'm going to use our Maclaurin series for e instead. So remember, e to the x is 1 plus x squared over 2 factorial, right? Plus x cubed over 3 factorial, blah, 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 right? Here, x is whatever's in the exponent. That's what goes here, right? Here, here, right? So this integration is the same as trying to integrate from 0 to 1 of what? What? What's the Maclaurin series for e to the negative x squared? 1 plus, now instead of x, what am I plugging in? Negative x squared. So I should have written minus there, shouldn't I? But it doesn't matter. I'm going to write it like that. Okay, that's this. Now what? Plus whatever we're plugging in squared. So what would happen if you squared this? You get x to the 4th. X to the 4th over, where are we? Here? 2 factorial. Okay, plus. Now, what if we cube it? What's negative x squared cubed? Negative x to the 6th, right? Over 3 factorial, right? That's where I am? Y'all following me? Okay, and then plus, let's see if we can get one more. The next one would be to the 4th power, wouldn't it? X to the 8th. Not 8. Okay, x to the 8th over 4 factorial. Any guess to the next one? Minus x to the 10th over 5 factorial plus dot, 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 right? dx. Right? Now, the great thing about this is that we can integrate this term by term, Just integrate them. So look, this should be equal to, remember how we did this when we had like integral of x squared dx? We would say 1/3 x cubed, and then we put the bar there, oops, 0 to 1. We put that little bar there, and then go 1 and then 0 like that. Okay, so first thing we did was find the antiderivative. So what's the antiderivative of this? What's the antiderivative of 1? X, okay? Now this one's a little harder. Be careful here. What's this going to be, antiderivative? Negative 1/3 x cubed, right? What about the next one? Plus 1 over 5 times 2 factorial x to the 5th. Do y'all buy that? 2 factorial is a constant, so it can just sit out here. Antiderivative of x to the 4th is 1/5, right? 1/5 x to the 5th. So I can just put it like that. And then what would the next one be? Minus, maybe like 1 over 7 times 3 factorial x to the 7. And hey, be careful. 5 times 2 factorial is not 10 factorial, right? And this is not 21 factorial. You have to do the factorial before you do the multiplication there. All right, let's go one more. Plus 1 over 9 times 4 factorial x to the 9th. I'll just do another one. 1 over 11 times 5 factorial x to the 11th plus dot, dot, dot though, right? Bar 0, 1. So what would happen is if I plug 1 in here, this would be 1 minus 1 in here, 1/3 plus 1 in here, whatever that number is, minus whatever that number is, plus whatever that number is, minus whatever that number is. And that series would converge to a number. And the number it converges to is the answer. And that's what Wolfram alpha did. In fact, I can prove to you that that's what it did by going back to the website and scrolling down. No, I'm going to go back up here. I'm going to take out the from 0 to 1. And remember how it gave us error function? Wolfram alpha is smart enough that it is willing to give us the first few pieces of the Taylor's. It says Taylor series, but remember, a square is a rectangle, right? So it's giving us the Maclaurin series, and the first 3 pieces of the antiderivative were x minus 1/3 x cubed plus 2 factorial is really 2, so this 5 times 2 is 10. This is 1/10 x to the 5th. See? It gave us the first 3. And then this right here is just telling you that, yes, there's a bunch of crap still out there, but it stopped at the 6th power of x. Like, it didn't go past the 6th. So it went out to the 5th, looked for a 6th power, there was none, and so it just says, yeah, there's a bunch of stuff out here. Right? So this is, ignore that. Make sense? Yeah? All right. So theoretically, if you can somehow take a function, find its Maclaurin series, then you can always integrate it, right? Because once you have its Maclaurin series, then the antiderivative is just power functions. There's nothing difficult about this. Yeah, these numbers suck, but otherwise it's just power rule over and over and over. And you only go out as far as you need to, right?
How would you expand that? The 7 3 factorial.
3 factorial would be 3 times 2 times 1, and then times 7. Yep. Okay. It's harder than it looks. All right, we have switched gears a little bit here.
So you said that if we found the Maclaurin series,
Maclaurin, yeah.
for something you can always integrate, but that doesn't always go for Taylor series.
No, Taylor also, because Taylor series, the only difference is that we're going to have like x minus a number in a parentheses, but you can still integrate that. Still power rule. Yeah, same concept. Yeah, Taylor series is super powerful in computer science because you can take any function, turn it into its Taylor series or Maclaurin series, and then you can do arithmetic to do any computation you want. You know, multiplication, division, so you can use a computer. Whereas if you don't have it, you just have to use integration by parts, trigonometric substitution, then you're relying on your brain, and that's a little bit less efficient than the computer's not going to make the mistakes. You know what I'm saying? So much more powerful. All right. Well, different game here, right? We're now doing a Taylor series. So things are going to be a little different now, and as you're going to see in this example, this one's going to work out. It's going to be a little messy. Okay, you ready? I'm going to do exactly what I did before. I'm going to make two columns. This is going to be the nth derivative at x, and then this one right here is going to be the nth derivative where? At a, and a for us is 3, because I tell us it's 3. I forgot to mention, we found the Maclaurin series for sine, cosine, and e, right? All three of them have a radius of convergence of infinity. So those power series or those Maclaurin series are valid for all x. Some power series or some Maclaurin series are only valid for certain intervals of convergence, okay? But those three that I showed you work for all x. All right, here we go. The zeroth derivative of this function is itself, 1 over x. No problem. So what do I get over here? The zeroth derivative at 3 is 1/3. All seems well so far. The first derivative of this function is negative 1 over x squared. So where is that coming from? The fact that this is really x to the negative 1, right? So the derivative of that, the negative comes out, x to the negative 2, and you get this, right? Now I'm going to leave it like that, but I'm going to rewrite it like this just so we know what we're working with here. That is this, right? Now what is the first derivative at 3? Negative 1 over 9. Agreed? Okay, keep it going. What is the second derivative at x? Positive 2, what? Over x cubed. So this 2 comes out, right? So positive 2 over x cubed, which is really, I should maybe write it like this, 2x to negative 3, like that. So what is the second derivative at 3? 2 over 27. You need to start picking up on a pattern right now. Does anybody see the pattern yet? Okay, it's alternating. The bottom are powers of 3. And there's a 2 here, there was a 1 here, there's a 1 here, there's a 2 here. What's my next numerator going to be? Negative 6, which is really, so I'm going to leave it as 2 times 3. Because when I come around for the next one, is it going to be 2 times 3 times 4? Do y'all see what's happening here? I mean, this is what I need you to start to see. This is, let's do it, okay? But I'm trying to get you to recognize that there's a pattern. The next one will be negative 2 times 3 over x to the 4th, right? Yes, I could put negative 6, but I'm trying to maintain the pattern in here. This is really negative 2 times 3x to the negative 4. And that's what I'm going to take the derivative of on the next step. And see, the 4 is going to come out, I'm going to 2 times 3 times 4. But I still need this. What is the third derivative at 3? So watch how I write this. I'm going to write it as negative 2 times 3 over what? I'm not going to put 20, not 20. What am I missing? Hold on. Oh, yeah, this is right. To the 4th, right? I'm going to put 3 to the 4th down here. Do y'all see that? And now I can like retroactively go backwards. This one is really 2 over 3 cubed, right? This one right here is really negative 1 over 3 squared and crap, okay. It seemed like it was working. Like this looked like 1 factorial, 2 factorial, 3 factorial, right? Well, that would mean that that one has to be what? 0. Oh, it is 0 factorial. See, it works. It happens to work out in this, doesn't it? All right, so we'll get to that. Let's do one more derivative. 4th derivative at x should be positive, right? This time positive. 2 times 3 times 4, x to the negative 5. I'm going to write it that way this time, which is 2 times 3 times 4 over x to the 5th. So over here, the 4th derivative at 3. Do you see how this is a little more complicated than like 1, 0, negative 1, 0, negative 1, right? Like this is a little more going on here. So we've got 2 times 3 times 4 over 5 factorial. No, what? Huh? What? The hell am I talking about here? Whoa. It was a good weekend. I had a good weekend, I guess. Now, why is it important for me to try and establish a pattern here? I need a general formula. Now, in the previous problems, we didn't need a general formula. The reason we didn't need a general formula is because we established a pattern that was cyclic. And once it was cyclic, we just wrote them out, didn't we? Now we can't because we have a pattern. So, can we come up with right now a formula for C sub n? Which, remember, would be the nth derivative at a over n factorial. That is the formula for C sub n, right? So do we have a formula for the nth derivative at 3? Do we have a general formula? Do you have an idea? Let's start. You already said it. Positive, negative, positive, negative, positive, negative, right? Would be the pattern. So if we want to start out with positive, we would have to use negative 1 to the n. Okay, that's going to take care of our switching. Now let's look at the numerators. 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So we should put what up here with it? N factorial, right? That'll take care of that. And then over, what's the pattern in the denominator? 3 to the 5th, but this is 4. 3 to the 4, but that's 3. 3 to the 3rd. So it's going to be 3 to the n plus 1, right? That way we get a 3 here, then 3 squared. Do y'all see that? Everyone see this? Sure? All right. So for us, in this problem, our C sub n, which was this, which was the nth derivative at 3, because we were told 3. And this is the formula we just came up for that. This should turn out to be negative 1 to the n factorial over 3 to the n plus 1 over what, though? N factorial. And do you see what happens to those n factorials? They cancel because this is the same as like this over 1. You can flip it and then the factorials will be gone. So these are gone, which leaves you with just negative 1 to the n over 3 to the n plus 1. Make sense? So far, we're not done. We just came up with a formula for C sub n. Now, the Taylor series. The Taylor series, remember, from the beginning of class, was this C sub n x minus a to the n, right? That's our general power series, but we have a formula for C sub n. We just found it's this. So our Taylor series for this is sum n equals 0 to infinity of this expression, negative 1 to the n, over 3 to the n plus 1, times what? Parentheses x minus 3 to the n. There it is. That is your Taylor series for 1 over x. Questions? I still want to do one more thing.
Is A something that's like for 1 over x, it will only be 3, or you just
No, I just gave us 3. It could be. I think there's a problem just like this in the homework where they use a as 2.
So A is just a value that anyone can pick?
Yep. Remember, all the a does is shifts over. Because our power series might have an interval of convergence, and we want to be looking maybe over there, but it's only converging here, by using a, that moves it over so it's valid within a certain range. Now, in your homework, when I work these problems, I take them to this point and I say, okay, now you can do the ratio, because in the homework it asks you to find the Taylor series and its radius of convergence. And in the homework, I don't do the radius of convergence, and I should say, I don't do it. You need to do it. That means you need to do ratio test on this to get your interval of, or radius of convergence. You know what I'm saying? Limit n goes to infinity, absolute value of this with n plus 1 plugged in over this with n plugged in, and yeah. So I would like us right now, with this little series here, I would like for us to just write out a few of the first terms, and I'll tell you why in a second. All right, so let's just write out a few of these. So let's plug in n as 0. If we plug in n as 0, what do we get? One over 3. X minus 3 to the 0 is 1, isn't it? So it's 1/3. We get 1/3. Okay, now the next one will be minus, won't it? Because now we're going to plug 1 in. 1/9. X minus 3 to the first power, right? Now we plug in n as 2. 1 over, positive 1 over 27. X minus 3 squared plus dot, dot, dot. Yes? All right, good. I just wanted to write out the first few terms. I'm curious if Wolfram alpha, let me see if it'll give me series 1 over x about 2. What do you think? I haven't tried this myself. Oh, 3. What do you think? You think it's going to know what to do with this? I have never tried this. Jesus. It was a little faster than us. Right? I didn't have this when I was in school, man. It would have been awesome to have something like this, just as a reference, something to check your work, make sure you're doing things right. There it is. Okay. So we have successfully found the Taylor series for that function. Doing good, doing good.
So for the test, for example, the final answer would be the formula, right? On that.
Yes, the formula would be the final answer. Unless I ask you for the first 4 terms of the series, then you would have to write out the first 4 terms. Which in the homework, I think there's some problems coming up where they do ask you to write out the first few terms.
And what were you mentioning about the ratio test?
you have to do the ratio test in order to figure out the radius of convergence on that, to see where that thing is valid. Because that power series we just wrote out would not be valid everywhere. If you ran the ratio test on that one, it would not be negative infinity to infinity. Does anybody know why? You could tell me that right away? Because it's 0. I mean, the original function was 1 over x, right? So you know you can't plug 0 in. So that power series will not work if x is 0. Okay. I feel like I'm missing something here. How about this? I'd like for us to integrate e to the 2x times cosine of 4x dx. Now, could we do this? Could we do this using what we've learned in this class? Integration by parts, probably several times in order to get it to appear on the other side. It's one of those ones where it won't go away, but it'll reappear, and we could probably work it out. Now, in your book, on page 484, I believe. Hold on, let me see. Yeah, on page 484, there is a table of common Maclaurin series, and I just told you about this a little while ago. I will provide you this table on the final. So if I ask you to do this integral like this, what I'm going to tell you is saying using Maclaurin series. And I'll tell you something like just first 3 terms, something like that. So this is kind of like the problem we just did a second ago, where we did e to the negative x squared. Didn't we use the formula for e to the x and write it out and then integrated it? You're allowed to do that here. You can use the formulas, but I have to use 2 formulas. I have to use the formula for this and then the formula for this separately. This is going to be messy, all right? But let me show you the idea here. What is the formula for e to the 2x? Well, that should be 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial. You all with me on that? Over 4 factorial plus dot, 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 right? That's what e to the 2x is. Now, what is cosine of 4x written in its Maclaurin series? So that's the cosine. You're going to write out the cosine series replacing x with 4x, right? So what would that be? So what's the series for cosine? Well, cosine's even, right? So it starts at 1. So it's 1 also, right? Plus, or is it minus? Sorry, alternates. Minus. So 4x squared over 2 factorial, and then it alternates plus. Now it'll be 4x to the 4th over 4 factorial, and then minus 4x to the 6th over 6 factorial plus dot, 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 right? Now, look at what we're trying to integrate. We're trying to integrate this times this, right? How do you multiply these 2 series together? That seems like a problem, doesn't it? Doesn't that seem like a problem? Well, I mean, like if I asked you to do x squared plus x plus 1 times x to the 4th minus 3x to the 3rd plus 2x minus 4. If I asked you to multiply these 2 polynomials together, how would you do it? you would do like here to here, here to here, here to here, here to here, right? Then you take the second one, go here, 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 and then here, 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 right? And you'd be done. But what if you have something here, and this goes forever, times something here that goes forever, you know? How are you going to do it? Like you go here times here, here times here, here times here, up, keep going, right? You can't stop, right? And then you go to this one, then do the same thing forever. You can't, you see? So the way to do it is that we're just going to do like this first one times the first few of those. This second one times the first few of those, stop. The third one times the first few, and we're just kind of get a feel for it. Does that kind of make sense? Because you can't go forever. So let's try this. This is going to be a little bit messy. Let me clean these up first a little bit, see if we can. What would this be equal to if we clean it up? 1 plus 2x plus, what would that next one be? Let's actually work this out. This is 4x squared over what? Over 2, right? Which is really 2x squared? Okay, what would this next one be? This is 2 cubed times x cubed over what? 3 times 2 times 1, right? How many 2's would be left on top? Because I have 1 2 on the bottom, don't I? Did y'all see what I did here? Yep, this 2, and that becomes a squared. So we have a 4 on top. 4x cubed over 3. Do y'all follow what I'm doing or no? Now I'm going to say plus dot dot dot. I'm going to stop there, okay? That's that one. Now what about the next one? This one might be a little bit messy. 1 minus 4 squared, 16, right? 16 over 2. 8? 8 what? X squared. And then plus, crap. This is going to be 4 to the 4th, x to the 4th over 4 times 3 times 2 times 1. One of these 4's cancels. What is 4 to the 3rd? 64, right? 4 to the 64. What's 64 divided by 2? 32, and then I still have a 3 down there. So I think 32 thirds x to the 4th. Y'all see what I did? Okay, plus, I'm surrendering, plus that, right? And now I will multiply these two together. I haven't done any integration yet, right? I haven't done any integration. I'm just multiplying them together now. Now you might be saying like, I'd rather have done the integration by parts. But if I change these functions into something else, like if I would have done e to the x squared instead of 2x, then you could still do this, but you couldn't do integration by parts. So, all right, I'm going to take 1 plus 2x plus 2x squared plus 4 thirds x cubed plus dot dot dot, and multiply that times 1 minus 8x squared plus 32 over 3x to the 4th plus dot dot dot, and multiply them. So this is e to the 2x times cosine 4x, right? That's what this is. What's my first term? 1. That's good enough, right? We're done? So here times here, we get 1. So this is equal to 1. Okay, what about here times here? Minus 8x squared. So watch what I do here. Minus 8x squared. I left a space here. Why do you think I left a space? For any x terms I get. Okay, now just hang tight. What's the next one going to be? Plus x to the 4th, right? I left another space for x cubes. That's what I get when I do that through, right? Now, move on to the next one. What would this through here be? 2x, right? I'm actually going to put that right here. So what I'm doing is I have a first row Now here's my second row, which is me coming through with the second multiplication. Then I'll have a third row, fourth row, and then whatever how many rows I have, I'll add them straight down. That make sense? Okay, so next one through there. What's the next term going to be? Minus 16x cubed. See, in the cubed position. You know what? How many terms did I ask for? The first three, right? That means anything that goes here, any constants, linear, quadratic, I don't need this one because I only asked for the first three. So I don't need to do this multiplication from here to here because that'll give me x to the fifth power, which is way out here. Does that make sense? So fortunately, I only asked for the first three. Now we need to do the next one though. What's the next one? Here to here? And that's 2x, just 2x squared, right? And that goes with this one. So 2x squared, I'm going to put it here. What would the next multiplication be with this one over here? Negative 16x to the fourth, which would be over here. That's past what I'm looking for, right? So is there any way to get any more x squareds? Because I'm stopping at x squareds. The next multiplication would be what? X cubed. So I'm done. Do you see that? I'm done. I've gone far enough because I've asked for the first three terms. So this should be equal to what? 1 plus 2x minus 6x squared plus ... Okay? Now you integrate it. So the integral of 1 plus 2x minus 6x squared plus ... is going to be x, I can't say that, x plus x squared, right? Minus 2x cubed plus ... That's the antiderivative. I hope that makes sense. Let's see how this does. Integrate e raised to the, what was it, 2x times cosine 4x. So if I ask the computer to integrate this, it's going to do a good job. It's going to figure it out. But I'm pretty sure down here there should be a series. Whoa. There we go. Series expansion, 1/10. Okay, so they've got a, we've got a constant. We're off by a constant. But you see this? X squared minus 2x cubed. See it? X plus x squared minus 2x cubed. You see how we've got it here? Now we're off by a constant, but we knew we would be off by a constant, right? Because we're antiderivative. It's always off by a constant. Now, yeah, we would have to do plus c. I want to look at something. Let's see if this works. I know it's almost time. Have I shown you all the worst math teacher? Yes. I have? Yes. Okay, so I did show that to you. Yeah, the old guy, right? So that worst math teacher, there's a problem. There's a step in there, right? Do I remember it at all? Yeah. Okay. Yeah, so the question, the actual question that he had was, how did you get from one line to the next? And he said, oh, you just divide. That was the professor's answer. Oh, you just divide. What he was doing in the problem was he was taking the number 1 and dividing it by a Taylor series. Okay? So how do you take a Taylor series and divide it into 1? That's what the student couldn't do. What I've shown you here with this example is how you multiply 2 power series. All right? Next class, we will divide 2 power series. That way you can see how to do that. Does that make sense? Okay. Yeah, yeah. Okay, so we have one more class. Next class, the goal is for us to finish 8.6. We have not finished 8.6, so we've also not finished 8.7. The homework you should be able to do from 8.7 is everything. Why does this not show? I think the problems are like 5 through 17 or something like that. Don't go past number 18 in the homework. That's for 8-7. For 8-6, I think, for 8-6 you could do 1 through 10 right now. That's it. All right, we'll be back. We'll talk about the final next class. Have a good day.
That's like freaking 10 out of 10. Does it?